We have two learning targets on page 692, or starting on page 692. We're going to find the measures of central angles and their intercepted arcs, so we'll have to know what those things are. And then we're going to find arc lengths. So notice that we're talking about the measures of arcs and the lengths of arcs. They're actually different things. There's two different ways to tell how big an arc is. One way is called the measure, one way is called the length. We'll get there. So, a central angle. If we're going to talk about the measures of central angles, we have to know what a central angle is. A central angle of a circle is an angle with a vertex in the center of the circle. Its sides contain two radii of the circle. So in the figure on the screen, angle ABC is a central angle of circle B because the vertex of angle ABC is on the center of the circle. Now, it's a pretty big deal because later on we're going to have angles called inscribed angles that behave differently. You must be able to not only recognize that's a central angle, but call it properly a central angle. Okay? Now, I don't remember if we talked about this or not, but the definition of a degree is that it's 1/360th of a rotation around a circle. Since that's the case, that means that the measure of a circle starting at A, going all the way around back to A, is 360 degrees, which then means if we divide our circle up into a few central angles, as long as those central angles do not overlap, if I add their measures together, I've got to get 360. Okay? In fact, if I draw in 1,000,000 central angles, as long as they don't overlap, when I find their sum, I will get 360. Seem reasonable? Okay. Now, let me jump ahead just a bit to this, an arc. An arc is a portion of a circle defined by two endpoints. Okay, think about it. Be with me here. Pay attention. An arc is to a circle what a segment is to a line, because a segment's part of a line with two endpoints. You can measure it with a ruler. Same thing with an arc. It's part of a circle, two endpoints. Later on, we're going to measure it with a ruler. Right now, we're going to measure it in degrees. Okay? Now, if we have points P and R, arc PR, look at the way you write this. Arc PR consists of P, R, and all the points in the circle between P and R. Now, let's ignore for a moment that we could have gone the long way around from P to R, okay? The book says a central angle separates the circle into two arcs with the measures related to the measure of the central angle. And here it is. The measure of this central angle is equal to the measure of the intercepted arc. Since we measure angles in degrees, that means we also measure arcs in degrees. If that's a 120 degree central angle, then that's a 120 degree arc. Questions? Okay, let me keep going. Everybody with me? A minor arc is the shortest arc connecting two endpoints on a circle. So look here at the figure. The red arc AB is a minor arc because that's the shortest way you can go from A to B staying on the circle. Okay? Now, the measure of a minor arc is less than 180. Okay? Here's why. Here's how I know. If I drew that in, the measure of that straight angle is 180, right? Well, won't the measure of the minor arc always be less than that, since it's less than half a circle? So the book says a minor arc is the shortest arc connecting the endpoints. It's also less than half a circle. Since it's less than half a circle, its measure is less than 180. Now, here's a part, and I've already told you this, but the book kind of hides this, and I don't know why. The measure of minor arc is equal to the measure of its central angle. The measure of a minor arc is equal to the measure of its central angle. So a minor arc is the shortest arc connecting two endpoints. It's less than half a circle. Its measure is less than 180. And its measure is equal to the measure of its central angle. Well, if a minor arc is the shortest distance, it kind of makes sense to call a major arc the longest arc connecting two endpoints on a circle. So you either have a minor arc or a major arc. Or you can even say it this way. If you have a minor arc, if you go the other way to connect the two endpoints, you'll get a major arc. Okay? So the minor arc is the shortest way, the shortest path from A to B. A major arc is the longest path from A to B. So it's going to be more than half a circle. So its measure will be more than 180. Make sense? Tandem. That's a good question. How do we know if we mean the short arc or the big arc? They have to tell us. They have to tell us with the letters. Okay? And here's the thing. If I write arc AB and I write arc ADB, that's when you go the long way around. So I'm looking right here at the middle figure, the one I just drew a big blue circle around. Arc AB is the shortest distance, shortest arc from A to B, whereas arc ADB, it means that you start at A, go through D, and keep going till you stop at B. Not all of them, one. Okay? So a major arc must, I repeat, must give you a point that the arc goes through. Got to. All right? Now, a semicircle is half of a circle. A semicircle is an arc with endpoints that lie on a diameter. Okay? So look at the figure here. We have two different semicircles. The red one we would call arc ADB. The blue one, I'm looking at the bottom one now, the blue one, we can't name it. We can't. To be able to name it, I have to put another letter on there. Now I can call it arc AXB. What do you think the measure of a semicircle is? And why is it 180? Because it's half. The whole circle is 360 degrees, so a semicircle's got to be 180 degrees. Okay? Questions? All right, let's do a few from your assignment. So, on page 696, number 1, we're supposed to find the value of x. And x is the measure of a central angle. Now, we know that if we add all the central angles up, as long as they don't overlap, we get 360. So we've done this kind of thing before when we're working with parallelograms and triangles where you know what the sum's supposed to be, so you'd subtract to get the missing piece. Same idea. 60 plus 130 is 190. So if I subtract 190 from 360, won't that tell me what x equals? And what is 360 minus 190? 170. You remember how, too, I said that when you subtract from 180 with the triangles, it's easy to be off by 10? When you subtract from 360, It's easy to be off by 10 or 20 or 100. Trust me, 100. You can do it. I make that mistake every now and then myself. All right, number 2. Now, I thought that the picture here was a little bit confusing with those arcs. I couldn't tell if that was one red arc or 2. It's 2. They're trying to tell us that the measure of this angle is also 35. Well, 35 plus 35 is 70. 70 plus 140 is 210. So won't x equal whatever 360 minus 210 is? 150. So far, so good. So finding the measure of a central angle, if you have enough information, not difficult. Now, let's start working on the measures of the intercepted arcs. A lot of times I end up saying corresponding arc, and that's not 100% right. They're intercepted. The central angle intercepts an arc. All right, look at the screen here. This central angle intercepts this arc. The measure of the central angle equals the measure of its intercepted arc. You'll hear me say that a million times. Don't forget it. The measure of the central angle equals the measure of the intercepted arc. So, let's see what's going on here. That's right. So the measure of arc, HI, is 59 degrees. So let's do number 4, okay? The directions say, identify each arc as a major arc, minor arc, or a semicircle. Well, that's definitely the shortest path from H to I. It's definitely less than half a circle, so that is a minor arc. Now, the little M in front of the arc means measure. Just like a little N, like if we had angle A, and then did that, that means the measure of angle A. Same idea. So that means the measure of arc HI, well, we've already found it. It's 59 degrees because it equals the measure of its central angle. Okay? Let's back up and do number 3. Number 3, they want us to tell them what kind of an arc IHJ is. Start at I, go through H, keep going until you get to J. Well, that's more than half a circle. So that's a major arc. Now, it's measure. I could piece together the measures of all those arcs, but you know what's easier? If I start at I and go all the way around the circle and end up at I, that's how many degrees? 360. So couldn't I just subtract that part out from 360? Yeah, that's a 90-degree arc, isn't it? Because the central angle's 90, so the arc's 90. So 360 minus 90 equals, so the measure of arc IHJ is 270. We can do what with 360? No, never get over 360. All right, arc, HGK. Start at H, go through G, stop at K. Now, they tell us in the directions that segment HK is a diameter. So what kind of an arc is arc HGK? It's a semicircle. And since it's a semicircle, what's its measure? Exactly. So what do you think so far? Pretty easy? Pretty easy. Okay. What's the measure of the central? What's the relationship between the measure of the central angle and the measure of the intercepted arc? They're the same. Don't forget that. All right. Congruent arcs are arcs in the same circle that have the same measure. Or they are arcs in congruent circles that have the same measure. So look up here at the figure for Theorem 10.1. They tell us that if the measure, or if angle 1 is congruent to angle 2, then the arc intercepted by angle 1 is congruent to the arc intercepted by angle 2 because they have to have the same measure, don't they? If angle 1 and angle 2 are congruent, let's say that's 70, so that's 70. Well, then that arc is 70 and that arc is 70, so they're congruent because they have the same measure. Now, another part of this definition is it can be arcs in different circles as long as the circles are congruent. Let me show you why the circles have to be congruent. I think you'll understand this pretty easily. I'll do that as the little circle. Oh, come on. Move that one up here. All right, look here. The circumferences of those two circles are nowhere near equal, correct? If I mark off a 90-degree arc on that circle, and I mark off a 90-degree arc on this circle, their measures are both 90. But are those two arcs anywhere near the same size? They're really not, are they? Okay? So we would not want to call them congruent. Now, that gets us to the idea of arc length that we're going to talk about in a minute. Sometimes it makes more sense to talk about the length of an arc than it does its degree measure. You with me? All right. Number 6 from your assignment. The graph shows the results of a survey taken by diners relating what is most important about the restaurants where they eat. Part A wants us to find the measure of arc AB. We'll look over here. Here's arc AB. And that arc is 22% of the whole circle. Look, they don't tell me any angle measures. There's not a degree mark anywhere on that figure. Okay? So I can't just do it like we've been doing and say, oh, whatever the measure of that angle is, that's the measure of the arc. That's true, but I don't know the measure of the angle. But the measure of arc AB equals. So, but, isn't the whole circle 360 degrees? So shouldn't the measure of this be whatever 22% of 360 is? Does that seem reasonable to you? Now, make sure that you change 22% to a decimal, 22%, 0.22, of. Sometimes we forget that of means times. Times 360. That's 22% of 360. And let's see what it is. 0.22 times 360, 79.2. Do part B. Make sure you write 8% correctly as a decimal. You get 28.8. Didn't use 0.8, did you? Yeah, don't use 0.8, 0.08. The last question. Describe the type of arc, meaning major, minor, or semicircle, that the category great food represents. Well, great food's 56%. That's more than half a circle. That's a major arc. So remember, major arcs are more than half a circle. They're more than 180 degrees. They're the longest arc connecting C and D. Okay? All right, you still with me? Now, something that if I never told you, you would have just assumed is correct because we've even already done it. Arc addition postulate. You can add up the measures of arcs, just like you do add up the measures of angles. Now, technically, here's how it works. Adjacent arcs are arcs in a circle that have exactly one point in common. So in the figure you see on the screen, point J is the one and only point that's in arc HJ and in arc JK. Since they have one and only one point in common, they're adjacent arcs. Well, if the measure of arc HJ was, let's say, 45, and the measure of arc JK was 55, wouldn't you expect the measure of arc HK to be 45 plus 55. Okay? That's how it works. It's called the arc addition postulate. If I'd have never told you that, you would have just assumed it worked that way, wouldn't you? All right, let's do a few more. These are our last few examples before we do arc length, which is a little bit different animal. So, they tell us on 7, 8, and 9 that segment QS is a diameter. Now, if that's a diameter, we know it divides the circle up into two semicircles. Find each measure. Usually, the easiest thing to do is to find all the measures and then answer their question. For instance, see the central angle that's 75 degrees? Means that arc is 75, doesn't it? See the central angle that's 72? That arc is 72. See the 90-degree central angle? So that arc is 90. Tell me, what's the measure of arc QR? It's got to be 90 because that's got to be perpendicular, doesn't it? Now, we've got one arc whose measure we don't know. Let's figure it out. Doing this, isn't this a semicircle? So 72 plus 75 is 147. So won't the measure of QP be whatever 180 minus 147 is? And what is 180 minus 147? What is it? 33. So look, now answering these questions is just going to be arithmetic. You with me? So, number 7, the measure of arc STP. Starts at S, goes through T, ends at P. Well, 72 plus 75, 147. Number 8, the measure of arc QRT. Starts at Q, goes through R, goes all the way around to T. Now, I could do some subtracting, but this addition is pretty easy. 90 plus 90 is 180. 180 plus 75 is 180 plus 75 is 255. All right, and last, the measure of arc PQR. So starts at P through Q, ends at R, 90 plus 33, 123. So sometimes our book names minor arcs with 3 points. They're not really supposed to, but they do. So we'll just get over that, all right? I'm the only one that bothers, aren't I? It does bug me, but doesn't bug anybody else, so I'll shut up about it. Arc length. Now, you got to pay attention to me here. This can be really easy. It can also be hard if you don't pay attention or don't think about this. Arc length is the distance between the endpoints along an arc measured in linear units. It's as if we could take scissors and cut the circle at the endpoints of the arc, stretch the arc out straight, and lay it down on a ruler. That's what arc length is. It's not the same thing as the measure, which is confusing, right? Because with segments, we can call it the measure of the segment or the length of a segment, and they mean the same thing. Not with arcs. The measure of an arc is in degrees. The length of an arc is in inches or centimeters or miles, whatever. Okay? Now, since an arc is a portion of a circle, its length is a fraction of the circumference. Think about it. If the arc was half the circle, shouldn't its length be half the circumference? And if an arc is a fourth of the circle, its length will be a fourth of the circumference? Make sense? Don't write the formula the book uses. I got a better one, and it's that. L stands for arc length. X stands for the measure in degrees. Measure is degrees. The measure of the arc. So that measure of the arc over 360, that's that fraction we were talking about, okay? And sometimes we'll need to reduce that, and sometimes we won't. All right, if it's a 90-degree arc, it's 93/60ths of the circumference. All right, now 93/60th reduces to 1/4. Sometimes if they ask for an exact answer, we'll want to do that. Other times we don't need to. We've got calculators. We can work with 93/60ths. Okay? Now, and then don't forget about capital C there for circumference. So we're going to have to find circumference. We did that in the previous section. We're going to have to do it again to do this. I like the top one. I really do, because we don't have to use 2 pi r for circumference, do we? We can use pi times diameter. So yeah, I kind of wish I hadn't put that on there, in fact. Okay? So if you can remember that arc length equals the measure of the arc over 360 times the circumference, you won't have any trouble. Now, I pulled a few here, not from your assignment, because I want to make sure we do enough examples of this. So this is 5A from the bottom of page 695, if you want to know where it came from. Here's how it works. They want us to find the length of arc AB. Okay? Here's what you write. The length of arc AB equals the measure of the arc. Now, the measure of the central angle is 45. So the measure of the arc is 45 over 360 times the circumference. Now, the circumference is 2 pi r, or it's pi times diameter. We almost always, they'll give us stuff, we can do it in our head. If the radius is 3, the diameter is 6, and if the diameter is 6, the circumference is 6 pi. Correct? We need the unit on there. Centimeters. Because not degree anymore, is it? Now we're changing it to a linear measure. Now, if you have a calculator that would do this, we can get the exact answer in one big step. Watch me. Parentheses. 45 divided by 360, close the parentheses, times 6, math, fraction, enter. Oh, it's 3/4. So that's 3/4 pi centimeters. Okay? But the directions, I covered them up here, tell us to round to the nearest hundredth. So I take the 3/4 times pi, and I get 2.36 centimeters to the nearest hundredth. You with me? Okay. Let's do 5B together. On 5B, let me scoot this over. All right, on 5B, the length of arc AB equals the measure of the arc, 80, over 360, times the circumference. Now, look, they drew a diameter in instead of a radius. So the measure they give us, the 14 meters, that's diameter instead of radius. It usually works that way. If they just draw a radius, the length they give you is the radius. If they do draw the diameter, they almost always give you the length of the diameter. Okay? So the diameter is 14, which means the circumference is 14 pi meters. So first, let's get an exact answer. So parentheses, 80 divided by 360, close the parentheses, times 14, math, fraction, Enter. That's 28/9 pi meters. But the directions do say, and we're going to follow the directions, to round to the nearest hundredth. So take that 28. And the reason I'm making you get an exact answer now, sometimes they ask you for the exact answer. Okay? So we got to be able to do that too. So take your 28/9 though. Oops, already did times. 28/9 times pi and 9.77 meters to the nearest hundred. Seven pi. Yeah. Do 5C. That one. Anybody able to come up with an exact answer without using their calculator? Sometimes it's not so bad. I mean, 120 over 360 is a third. You know, other times it is bad, but oh, that was stupid. Well, now what did I do? 16 thirds times pi. There we go. I knew I could do it. So that'd be about 16.76 feet when we round to the nearest hundred. We doing good? All righty. Prove it. Do number 10 from your assignment on page 696. Find the length of JK, round to the nearest hundredth. And yeah, we're almost done. You get 1.05 feet to the nearest hundredth. You able to do some of that without your calculator? All right, do 11. I dare you. The radius is 2, so the diameter is 4, so the circumference is pi times 4. All right, do 11. Now this time they give you the diameter, so don't double the 15. You get 13.74 like I did. So your assignment is page 696, 1 through 24, 26 through 43, 55 through 58, and 63 through 66.